So after we solve the coefficients, and we can just construct this polynomial case expansion for any of your random output. So even with this expansion, you can obtain the PDF of your output just by sampling the random variables in this expansion. Because this expansion is explicit once you get it, so you can have the statistic evaluation of your output, and we can also have analytical results. For example, you can calculate the mean value and the variance of your output. So we apply this method to multiphase flow equations. The multiphase flow is governed by this continuity equations. Here we have water, oil, and gas, and we substitute the Kerr expansion to this governing equation for the permeability function. In this form, you can see that these equations are very similar and equivalent. So we can just run our simulation using the standalone simulators. This problem is a SB-nice model, which is a benchmarking model used by different companies to compare the Reservoir simulators. We choose this model because this is a 3D highly heterogeneous reservoir. It's a 3D digital reservoir, you can see, and with water encroachment in the bottom, there is an aquifer in the bottom of the reservoir, and it's a three-phase model with water, oil, and gas. We can look at one realization of this permeability field. And this is just one realization. As we mentioned before, there are a large number of realizations in the random space. So we use the polynomial case expansion and PCM method compared with the Monte Carlo method. Monte Carlo method is just a straightforward method. You just generate a large number of realizations and perform the simulations and do the statistical evaluation, but it is very computationally demanding. So let's look at the PCM. Here is one representation of the random permeability field. We call it as a representation because this is not a real realization. It's not a real permeability field. This representation just corresponds to the collocation points. For example, we choose 231 collocation points. So we have 231 its representations and run the simulations independently. And in Monte Carlo simulations, you just choose 1,000 realizations. This is the minimum number to get the convergence. So let's look at the uncertainty. How much uncertainty in your production? We build up the confidence intervals for the oil production and gas production. You can see that the range is pretty high. And these two methods match pretty well. And we have to emphasize that our method just uses 230 simulations, and Monte Carlo simulations at least requires 1,000 realizations and simulations. So we can also look at the detail of your reservoirs for the flow simulation. You can have your oil saturation, you can have the mean value and standard deviation at different locations. Also, you can look at the gas saturation in the reservoir. This is the uncertainty you have. So, in summary, we propose the parameterization method, use the Kerr expansion to represent the Gaussian random field, and use the PCM, which is a straightforward method. It's non-intrusive to the reservoir model, and the existing simulators can be used to quantify uncertainties. The PCM is efficient because it builds optimal polynomial proxies based on this orthogonal functions. So while it is similar to the Monte Carlo method, and PCM is much more efficient for uncertainty quantification for the large large-scale problems. And the future work will apply this method to long Gaussian random field. So that's my talk. This is the reference. And thank you for your attention.
Go back to your first slide, please. Not the title slide, but the next one.
The first one?
Yeah. No. Please, I meant the first slide where you start defining the problem. Next. There. Okay. So, I understand X in physical space.
Yes.
Omega in random space. What do you mean by that?
Actually, we mentioned
Omega in random space, that phrase, I just don't grasp.
Okay, actually this y is the spatial function. Actually, x is this physical space. It's just.
I'm focusing on omega in random space. Those
So
are things.
yeah,
What
because
does that mean?
because this is a random function. So you have two dimensions. One is in the physical space. That's in the deterministic sense. But in our case, we have a random function, so we have a random dimension. So omega is representing this random dimension.
What is it?
That's for example, you have a random number, you have a random number, you have random dimension. That's your random space. Because for each of these locations, it's not deterministic. It's not one value. You have, for example, you have thousands of values. So that's the random dimension. It's kind of a stochastic process.
I understand square set processes quite well,
Yeah.
but I still don't understand what is omega in random space.
So you can just imagine for each specific location. So your x is fixed here, but your omega is changing, right? So that's the random variable.
Can you give me an example of an omega?
This one is just a definition. For example, I can just, if you run the Monte Carlo simulations, you run
I'll
just...
try one last time. You say X is in physical space.
That's
I think
right.
all of us sitting in the audience would understand we live in a three-dimensional world, and therefore X is some vector coordinate in that three-dimensional world. Right?
Yes.
Good. So what is omega? Give me an example of what is omega.
Okay. Because x is easy to imagine because it's physical space. But omega is just, you can imagine another dimension. For example, you can imagine a 4D dimension, right?
I can
That
imagine
one
all kinds of things. Could you just give me an example of omega, yes or no? It's not fine.
All right. So in this one, we can just define a random variable. You can just imagine like a random variable for specific locations. And this variable has infinite dimension. So I cannot give you just one example for this. So basically, it's a random function, and it has infinite dimensions.
Well, any other questions? If not, let's thank you again. Thanks, Amy.